Okay. Okay, let's talk about our fourth project. Okay. So this is about differential equation, and I'm not going to explain everything in single variable calculus. Some of them will appear the next time when we talk about the differentiability and differential of the multivariable function. Here, I want to emphasize some drawings in 2 dimension and how to solve differential equation numerically. So here's the definition of differential equation. You probably learned in engineering mathematics, but I'm doing it again in any way because from the morning class, I let students to think about setting up the differential equation, and not many people actually know or remember how to set the differential equation. So we'll do it together. So what is the differential equation? So it's an equation about function and its derivative. So here the function is the single variable function, takes a single input variable and single output variable. So here I want to talk about the first order differential equation, meaning that it's about the first order differential of the function. And its equation consists of input variable x, output variable y, and the variable that represent the differential of that function, y prime. So here is an example. When you have a free-falling situation, you can model this situation as a velocity of the object that is falling, as in here I call it v, and t is the time, the input, and I want to know how fast does this object is falling at a certain time. So here are some hypotheses, physical hypotheses and principles. So what we can do is set up an equation such that v prime, which is acceleration, is given by 9.8 times some 0.1 times v squared. So this all depends on the hypothesis, the physical principle. And if I may, I can, this 9.8 is the gravitational acceleration constant, and this minus part is because of the air resistance. There is a drag force, and when you have a falling object, it usually have a high speed, and the usual rule of thumb of the resistance force is that if your speed is fast, then it usually the drag force proportional to the square of the velocity, and 0.1 is the proportional constant. So this is an example of first order differential equation, but many physical situations cannot be described in terms of the first order differential. For example, the spring oscillation is the second order differential equation, but I'll explain how we could how we could break down into a system of first order differential equation. Now, x here is the displacement of the object from the equivalent point. So I put the spring in a horizontal way so that you don't have to think about the gravitational force. But even though you have a moving spring, but if you let it move for a while, it will stop because of the friction, and that is the place where there is no spring force applied. So that's the length of the spring, its own length, the spring's own length. Now, if you start to move the object hanging on the spring like this, then the position of the object is moved from the left or right. So when it's moving right, it's stretched. When it's left, then it's compressed. So depending on the x, it could be positive or negative, the spring force applied to the mass so that it is counteractive to the movement. So that's how we get this equation. X is the displacement of from the equilibrium position. And let me give you the idea why we get this equation. That might help later when we discuss how to set up the spring motion, spring pendulum motion. So this is the net force. This is the net force applied to the mass on the spring. And what is the spring force? Spring force always applies in opposite direction to the position of the object. So if the position is positive, the x is positive, then it's stretched. So spring tries to drag the object back to its original, so it always applies opposite direction. So that's why you have to take the minus. And then there is a friction, maybe friction of spring or friction from the ground. Anyway, also friction applies to the opposite direction of the movement in this case. So friction applies because the object is moving. So normally, as I said, if the speed of the object is fast, then the resistance force is proportional to the square of the speed. But in the spring motion, we assume that the speed is not that fast. So it's safe to assume that the resistance is proportional to the speed. So this is the equation. And if you put the right-hand side to the left-hand side, then you get this equation. So that's the spring. And there's another type of motion that you can write as a differential equation, which is the pendulum. So think about the pendulum is hanging on the ceiling, and here is the theta changes over time, and there is the length of the pendulum, and here it's fixed on the ceiling. So in order to simulate, in order to figure out the position of each mass, of the mass at each time, we need to know the angle for each time, right? So the angular velocity or angular acceleration is theta double prime is depending on this equation. So this is also second order differential equation, but we're going to break it into the system of first order differential equation. All right. Oh, okay. So by the way, why is this differential equation make sense? Why does pendulum move anyway? It's because of the gravitational force. So if you assume that this is our gravitational force, then it's moving in the direction perpendicular to the pendulum, right? So how much portion of this force? This is mg sine theta. So this determines the angular acceleration. So actually it determines the acceleration of the object moving in the two-dimensional plane. So roughly, if you take the distance that the object is moving at a certain time, this is the acceleration, and this is determined by minus mg. So I'm sorry. So m part is not important. So I'm just thinking about the acceleration. So I don't need m here. So sine theta, and therefore I get theta plus g over L sine theta equals to 0. So that's how you get the equation. Again, by the way, this theta, this equation is not only about theta, it's about sine theta, so it's nonlinear differential equation. So we're not going to go back to the engineering mathematics and try to solve by hand, and I personally don't think solving in hand is not the way we should learn or approach to differential equation, because most of the differential equation that you might encounter in real life is not something that you can solve in hand. So we're going to use the numerical algorithm to find the solution. So we need to understand the meaning of the solution first. So as I said, the differential equation is about the variables that determined by a function. So we need to know what the function is like, but usually we think about function as some sort of a formula. Function is not a formula. Formula is one way you can represent the function. So function could be represented as a graph, formula, table, data, sentence, whatever you want. So here we think about the approximation of the graph of a function this way. So we want to visualize or graph the function over a certain interval of the domain, let's say A to B, and I just want where my y values are located at each point in this interval. So I'm going to split my interval into array of x values equally spaced, and then I just need to know what I need to know is what's my value of function at each point on this lattice. So starting from y0, so it's going to be end at yn. So if I split it into n subintervals, there are n plus 1 data points on x-axis, and there are going to be n plus 1 data points on y-axis corresponds to each x. So how are we going to determine each yi? First, we start from the index 0, the first point. So I need to have an information where the functions start. So A is the starting point of x, and I need to know at that point what is my y. For example, if I have an object falling from the sky, I need to know what's its initial velocity, because the rest of the velocity, rest of the situation determined by the initial velocity. So as long as I know that information, now I have to estimate next y data based on the differential equation. So for example, let's say I have explicit formula of y prime in terms of x and y. Okay, so if I going back to the free falling situation, that could be explained like this. V prime is determined by formula of v and t. So here we don't see the t terms here, but it's there only that the coefficient is 0. So once you know what t and v is, you know what v prime is, and once you know what v prime is, you can estimate the next velocity of your object after a certain period of time, because v prime is roughly the rate of change. It gives you how fast the value of function increase or decrease over a certain period of time. So once I have this, then I can take the a comma y0 and then take the rate of change here at here, and then move my y coordinate or add to y0 amount that I need to increase by these formula. So this is going to be the y1. So I have at each step increasing the x coordinate by delta x. Delta x is fixed, delta is constant. If I fixed my number of subintervals, then it's fixed as a constant. So all I need is, since I know the rate of change, I need to multiply that rate of change with the x increment to get the increment of y. So if that value is negative, that it's not an increment, it's a decrement anyway. So this is the increment of y from y0 to get the next value of y. And then what I do is thinking about y1 as my next point, I mean the point where lies on the graph of function. I think about the rate of change at this point again, so at x1 and y1, and then think about how fast does the function increase at that point. So that's given by this formula. And then multiplying delta x gives you the increment of y. So if I add that increment from y1, I get the next y. So if I do this n times, I end up getting some value at the last step as yn. So in the meanwhile, I always get this discrete array of values, and this is going to be x and y coordinate of the point lying on the graph of the solution curve. So this is how you can think about getting the solution. The problem is there's an error, because each step I estimate my next y value simply by taking this curve, the solution curve, as if it's a linear line, right? But it's not always linear. So there are errors in between actual curve and approximation line, and these errors accumulates as I move forward. So at the end, you might not get the answer that is closer to the actual value. So you have to, there are many other algorithms to get the better result. One of them is the Runge-Kutta method. So seems complicated, but it's not. It's a relatively simple algorithm. So I'll explain how it works, but basic ideas are the same. So we're going to split the entire domain of x from n subinterval. And then for each step, I'm going to estimate the next value of y. So let's assume that I am at the nth step, nth point. Okay, starting from the 0th point, I am at the nth point. So how to estimate n plus first point from there? So I'm going to draw a big picture here. So here, big, and this is my xn, and this is my xn plus 1. So assuming that I already know what yn is, I need to know where my yn plus n is, n plus 1 is. So first, what I do is take the rate of change at here. So I need to know how fast does the function change when x is xn and the value of function is yn. So let's say this is kn, the slope is kn. If I just follow this slope up to xn plus 1, that's going to be my Euler method. But I'm not gonna do this. Just take the k1, and I only move halfway to the xn plus 1. So I'm here. I'm gonna stop here. Okay. So at this midpoint, I got this midpoint by following the first slope. Then I get the next, and then I compute the slope at this point. So here I get the slope. I compute the slope again. So k2. Okay. So maybe I should draw in different direction. So let's put it this way. So here, let's see, this is k2. And then what I do next is I take this slope back to the first point, xn and yn, and then follow that slope, follow this slope, and move halfway distance. Okay, so I'm at here, and then I compute the slope again here. It's going to be my k3. And then finally, I move my entire distance from xn to xn plus 1 by this slope, so k3 here. So k3. So I think let me color differently. So this one, k3 is this one, and then I follow the same slope all the way up to xn plus 1. Okay. Now, then finally, so it's not over yet. Then finally, I take the slope here. So that's going to be my k4. So k3 is here. So now we have 4 slopes measured in 4 different places. Okay. I'm going to take the weighted average of these slope to get the accurate slope to get to the next point. So the weight is given here, 1, 2, 2, 1, and you add it 6 times, so you divide by 6, and then this is going to be your slope that is supposed to be the accurate estimate of your next point. And then you multiply delta x to get the increment of y and add that to yn to get the next value of yn plus 1. So you're coming here, and then average slope, let's say, would be something like this, or maybe not this one. Let me write this somewhere here. So this is the weighted average of k. And then this is going to be your yn plus 1. So you can see that you're not just taking one slope. You're considering all the different possibilities. So there's no mathematical rigorosity why this works, but usually it works. And this uses 4 slopes, so it's that's why it's called the Runge-Kutta of degree 4. You can have an increased number of slopes to get a more accurate result, but this Runge-Kutta is quite good, considering that it only uses 4 times more computation than the Euler's method. So let's see here. So this is the result of Euler and Runge-Kutta method applied on the spring oscillation case. So I set my MV and K arbitrary number, and on the right you see the graph of the points obtained from the Euler method and Runge-Kutta method. The blue one is Euler. The dotted black is the Runge-Kutta. So, and Runge-Kutta is actually the same curve, so that you don't see the difference as the original solution, which I could get by solving by hand. So it's as accurate as you cannot tell the difference. So Runge-Kutta is always the best. Now, the problem is, how do we apply the second order differential equation to any of these Euler or Runge-Kutta method to find its solution? Because Runge-Kutta method and Euler method both are for the first order differential equation, because we can only get the slope, the rate of change, which means it applies only when we have a first order differential equation. You have to split that into two pieces of first order differential equation. So the way you can do that is setting up 2 variables, y1 and y2, representing y and y prime. So, and then think about this y1, y2 as a vector, or you can consider as a point on 2-dimensional plane. But anyway, what I need is, at each step, how fast or in which direction should I move my value y1 and y2, so that I get the accurate result. So that's going to represent as here. So y1, y2 prime is the rate of change of each coordinate. And if you combine these two, then this is the direction of y1, direction. Okay, so y1, y2 at the nth step point to move in order to get the next one, y1 and plus 1, y2 and plus 1 point. So if you keep doing this, then you get to the final point. So now I'm assuming that y and y prime is a function of t, but there's no t on the formula, but it's there. It's simply, it's the coefficient 0, whatever, how you think it's there. So let's think about the formula here. So y1 is y, and y1 prime therefore is y prime. So we already set the y prime as y2, so that's here. And y2 prime is y double prime, and we have the explicit formula of y double prime from the original differential equation. It's here. Okay, so you can consider the formula of y and y y1 and y2 prime as a function of t and y1 and y2. So here I'm going to write y1, y2 as a coordinate of y vector. So you can write as a y prime equals to f of ty. The same formula we described in the Euler method and Runge-Kutta method. So you can just plug here your situation to get the numerical solution. So you can apply this to the same pendulum motion. Here I have theta as y1 and theta prime as y2. So same thing applies here. And the picture you see here is the Euler method, the result of Euler method and Runge-Kutta method. The Runge-Kutta method is way better. And Euler method is actually something that you shouldn't use here because the error is too big. You can see the scale of y that this error cannot be accepted. So anyway, that's how you can work. So what we are going to accomplish in this fourth project is something like this. I'll show you the moving picture here. Something like this. So you can see that there is a spring oscillation and pendulum motion. So I didn't put the objects as a picture, but you can try to put some nice picture for the object. But anyway, I want to think about, I want to simulate this physical situation. So we talked about how to draw the coil. So what do we need in order to get this kind of picture or moving picture is that we need to know how to draw the coil at a given point, because I have the fixed point at the top, but all I need to know is how to draw the coil if I know the endpoint, another endpoint. And then another thing that we need to know is how does this endpoint move around this two-dimensional plane. So we need to solve, first we need to set up the differential equation based on our physical principle, and then we need to solve the differential equation to find its x and y, to find its location. Then we have to put it together to make it into a nice moving picture here. Okay, so I'm gonna give you time to think about first, since we already talked about how to graph this coil. I'm not going to do this again. Maybe you can think about on your own. Let's think about how can we write the differential equation. So here I'll draw the picture for you and give you time to discuss. So you can think about this situation on your also not a line. So this is a spring here. So we have an angle theta, and we have a mass, and you have a spring constant K, and we have proportional constant B for the spring resistance, or you can think about it as a air resistance. And in this case, set up the differential. Oh, I forgot to mention one thing. So B is the proportional constant for the resistance force in the spring. and x, so it's a constant, but x is the displacement of the mass from the equilibrium position. So our task is to set up the differential equation in terms of of function theta t and xt. So that's your first task to discuss in your group. And the second test is once you, or maybe you don't have to assume that you already have a differential equation. So from the theta and x, maybe x is not a good way you can do it. So let's say x here, L here, let's put it L. So length, so the displacement, maybe it's a little misleading. So small l, okay, so small l is the displacement from the equivalent position. Set up the function xt, yt, that gives the coordinate of the mass using in terms of theta and L. Okay, so there are two tasks. So first, find out the differential equation. Second, set up an equation of x and y in terms of theta and L. Then you get all the ingredient to draw the simulation. Okay, so before we begin, is there any questions? Is there any question on the slide? No? Okay, so as you can see, I brought rolled paper here. So I want you to, each person on each group come out and then take the piece of the rolled paper. There's a scissor, you can cut whichever you want, how much you want. So, and also pick up the pencil, a pen, the color pen, and then take your paper and pen with you and then try to use this for brainstorming and discussing, okay? So I've seen many of you using the pad, but I don't think the pad is the best way you can communicate. So let's try this. So one person for each group come to the class and then take the piece of this paper. Here. So don't take the entire pen here. Just take the take the same number of pen as number of your member in the group. Currently here. So if you have only 2 members in your group right now, then take 2 pens. Okay. Okay. There is no single method of solving this, but I think it's good time to take all the ideas together and see how a group did. Okay, so the we want to see how it looks like, right? So once you take the differential equation, then the next step is you have to test out whether your equation is correct. So let's see. I want to think about the movement of the pendulum, spring pendulum. So I'm collecting all the ideas. If I am missing something, you can point me out. So I'm going to take LT slightly different definition of LT slightly different than before. I'm going to take this as a total length, so LT here. Okay. Or maybe I just keep the small l instead. Small l here. And what I'm going to do is first let's pick up the equation for xt and yt, because assuming that we know that this zeta is a function of t, what is xt? Lt times, is it too obvious? Sine t, sine theta t, and then what is y? So if we take this as, let's say, x0, y0 as the tip of this pendulum, then I have to change this part also. So this is going to be x0 plus this, and y0 plus lt. Oh, actually, it's minus. Right? So once we know the function theta t and lt, then we can find out the endpoints, and it's a matter of drawing the curve, drawing the springs from these two to this. Okay, so LT is the total length of the spring at time t. So let's pick up the differential equation. So what you need to is you have to separate these two pieces of forces, right? So this one we have mg, and what about this part? mg cosine theta, and this part mg sine theta. Okay. So for the pendulum, I just need L double, so LT theta double prime t. So that's the acceleration of the object that is moving on the pendulum in this direction, this direction. So that's going to be minus the mg, no, not mg, so just the g sine theta t. So if you want to take consideration of the drag or the resistance of the pendulum, then you can take out, let's see, c times theta prime t as your resistance force. So in this case, if you have this equation, then the pendulum will slowly decrease its amplitude of angle distance, angle displacement. So it's gonna stop. So that's the pendulum motion, right? Everyone agree? Or any other thoughts? Okay, so let's think about the spring motion. So let's take L double prime T. So that's the acceleration, M L double prime. That's a net force. And let's take all the forces affecting on the object on this direction. So first we have mg cosine theta. So I can take away this t part, just make sure it's simple. So just take out all the t parts here. And then what other forces are there? Drag force or resistance, B L prime. And how about spring force? How much is the spring force? So K times what? Is it L or L minus something? Okay, so L minus L cosine theta. So I need to measure how much it's dilated or compressed from its original length, right? So let's take original length as L. So L is the original length of the spring. Okay, that makes sense? All right. So we have these two sets of equation. Now you need to make it into set of first order differential equation, right? I'm going to set 4 value y1 to be L, y to be L prime, y3 theta, y4 theta prime. So then y1 prime, y2 prime, y3 prime, y4 prime is what? First one is y2. Second one is, sorry, yeah, so second one is G cosine y, can you say out loud? What is it? So we have a theta here. So I moved my m to the right hand side. So we have y3 minus b over m, y2 minus k, y1 minus L. Okay. So how about y3 prime? It's y4. So how about y4 prime? It's G over L. What is L? Oh, just y1. Yeah, the meaning, it's not displacement, it's the actual length. L is the length. So it's cosine y3. Oh, sorry, sine. And then y1 c, and theta prime is y4. So this is the equation. This is the equation we need to solve. So once we find the solution, I don't care about y2, y4. I only care about y1 and y3 over t. So x is going to be x0, y1, cosine, is it? Yes, cosine y3, oh, so y is going to be y0 plus, so it's actually, yeah, notation is confusing, but I will just finish writing y1 Actually, this is sine. This was sine, right? So this one's sine, cosine, y3. Okay, so I want to draw this point. So let's try. Okay. So I'm going to use the code that I already made. Sorry for that. I'm not going to do everything again because I already have a nice thing here. So what I'm going to do is, okay, so I'm not going to use the Euler. I already implemented the Runge-Kutta, and I'm going to use this. All I need to do is set up the differential equation. I mean, set up the equation that determines the rate of change. So the first one was, so here you have to change the index starting from 0 because all the Python index start from 0. So what you see y1 is actually y2. And here we have g times cosine y3 is 2, y2, and minus b over, so this b is this over m times y2, but y2 is 1, y1 here, k times y1 is y0, right? So y0 minus L0. So L0, well, you can just put large N, not to confuse. So L, and then that's the second one. And then third one is Y4, which is Y3. And the last one is G over Y1, which is Y0, and sine Y3, which is Y2. And then let's put more thing here. Y1 is y0, and times y3. Okay, I need to put c here. Let's see, put c as 0.5, same thing as b. Now let's solve it. So I need to give the initial condition in order to solve numerically. So y1, y0, 1, 2, 3 are L prime, theta prime. So originally L is 7, and L prime, which is the velocity of the spring motion, will be, let's see, how should I put it? So L, okay, so the original length is 5, so when I put the initial length to be 7, it's already stretched. So I don't think I need to put any excess velocity here. So theta is starting from 0.5 radian, and I don't want to make it move. So 0 for the theta prime. And then I implemented my Runge-Kutta so that it takes 2 more arguments. The second one is the step size, so like delta x. And here I think I should go back to, so it's the endpoint of x. So it's 10. So always start from 0, and it will move by 0.1 step each time. Is estimating for the y value, and then it stops when x becomes 10. Okay, so once I've done that, then I get the range of t and range of y. So here range of t is the range of time, and y is the array of vectors. I want just the y0 and y2 because that gives you L and t, L and theta, right? So let's see. This is L and this is theta. So I put my start and start y to be 0, but I have to add this to here. So start y here. And then let's make it move. So here we have plot situation, and here I have, so I tried to make it a moving picture. So I imported another package for saving of image as a GIF file. So I will upload this file on the Colab, so you can download, you can just copy paste into your computer, or you can just run that in the Colab. But make sure that you installed this package using pip. So then let's see what happens. Oh, something weird going on. So it's something weird going on. So let me pause here. So I don't want to show it. I want to see it in a GIF. So once it's done, it's gonna saved in here. Yeah, it's the same figure. Something is wrong, so you have to do it again. Find out what's wrong. But so I've seen that someone tried a different way. So you have to check by looking at the result again. So since we have time, let's try to review what went wrong. So I think I just go over to this part. So I don't think there is any problem on the numerical algorithm. So here, let's see. L is supposed to be 5, and I stretch to 7. And sometimes the problem is I stretch too much, so it goes, bouncing off the ceiling. So that might be the problem. So I'll put it as 6, a little bit of stretched, and K. Let's see. I want to make K a little bit bigger so that it doesn't oscillate too much. And also it could be a problem of the gravitational force. So I put G, the actual value, but I think if I put the actual value of gravitational force, then it might say like this. So this 5 is a unit of meter, and this 2 is a unit of Newton per meter. So that might be a problem, but I'll check what would happen. So let's see it here. So it's not work. So a little bit different before. So but still not as good as what I'm expecting. So something is wrong in the pendulum motion, right? I think maybe is it because of a dragging force? Oh, I think I should. Oh yes, I think I should consider the L part. So yes, I think I should take L here, because I'm looking at the speed, not angular speed. Okay, so then I have different equation here. So instead of dividing y0, I just have this. So let me see. Oh, okay, so I think spring constant is too small still. So I think I'll change it to 5. Okay. Okay, so 5 is good enough, but I can make it a little bit bigger. 7 maybe. Okay. So you can see that spring motion also stabilizes into a certain point, and also the pendulum motion stabilizes to what? I think it should stop at a certain point, right? Oh, okay, so it was repeating. Okay, so yeah, now we have it. So maybe I can a little bit make it longer, like 8, and this is 9. So then you can see it a little bit more longer version of the spring. Okay. So if you want to let it move for longer period of time, you can change the input in the Runge-Kutta here. So by the way, so maybe I'll just copy paste the code here. So that you can do it on your computer. I'll share this link, and here. Okay, so I just updated my Notion, so you can go to Notion site, and then you can copy, and this one works on your Colab because it only saved it as a oh, this is not it. So this one is saves it on the computer. So here, what you need to do before you run this code is installing the image magic here. So you can copy paste this command, this exclamation symbol, and pip install this one. And if you hit enter, then it installs this package onto the cloud environment, and then you can run this code so that you can save the result in a zip file. So yeah, so try on your computer or on your Colab with a different formula, maybe different value for the constant, and also maybe change the change the starting point and do something else, and or you can try to put some figures on the end of the spring if you want. So if you run this code, I think it saves on the cloud storage here. So here is, so you can see it here. The result goes here. You can open up the GIF file here. Okay, so raise your hand if you're doing spring oscillation. Where is the group doing? Okay, so you guys can try more than this one. Okay, so we already implemented 2 motions here. You could think about double pendulum, double spring pendulum. So double pendulum also has a cow's motion, but maybe if you incorporate double spring pendulum, that might be more chaotic. And or you can think about making into some kind of interactive game. So here it shows you a picture of determined by the input values. So you might want to ask user to input data that determines the motion, or you can allow user to use mouse cursor to drag the spring at the first time, and then when the user lets the mouse button go, then it starts to move. That kind of game, or whatever you're trying to do, make it as in the output. And so this is the 4th project, and I'm thinking about for the second project, start from the 5th project. So fourth up to 4th project is not going to be an option for your next project for the next half of the semester. But if you have a good idea to do the 4th project, then I might consider allowing you to do this. Uh, but otherwise, this is it. And from next time, we're going to talk about the differentiability of the 2-variable function and 3-variable function and the meaning of that. And so we have Friday, next week Friday, for pre-presentation. So you have to upload your work on the Notion. So at least upload whatever you want to give a presentation to the Notion. And don't try to just copy paste the code. Okay, so if you need to show the code, then just copy the core part of the code so that everyone can see clearly what that is. Because if you just paste the entire code, nobody can read it. And all right, so that's it. And if you have any questions, let me know, and we'll see you on next Wednesday.